Okay, before we get into the index of hydrogen deficiency, we're going to talk about our organic families of molecules, again, the homologous series, because it's important that we know what they're all called and how they're going to show up for this index of hydrogen deficiency. So I'm using just 3 carbon examples just so that we have molecules to look at when we talk about that index of hydrogen deficiency. So as a reminder, you've got a bunch of different hydrocarbon groups made of just carbon and hydrogen, alkanes, alkenes, and alkynes. Functional groups are the alkynyl group, the alkynyl group, which is the C to C double and the C to C triple. Molecules you don't usually have to name, but that you'd be expected to understand if you saw them or you heard them mentioned are cycloalkanes, so ring alkanes where all the bonds are single bonds. Cycloalkenes, so again rings, but they contain at least one alkenyl group. And then there's benzene, which we know is C6H6. Usually on the IB exam, it's going to show up as this hexagon with a ring around it to represent the delocalized pi electrons. You also see it represented as alternating double and single carbon-to-carbon bonds, but we've talked about how the ring is a bit more accurate. We've got halogenal alkanes, so alkanes that have halogens on them. There's a whole bunch of oxygen-containing groups. There are ones with only single bonds, so those are alcohols and ethers. We've got aldehydes and ketones. They can both contain a C to C double bond. And then we've got carboxylic acids and esters, which contain 2 oxygens, 1 double bonded and 1 single bonded. There's also a few nitrogen-containing groups to know. There's the amines, which have nitrogen somewhere on the chain, but it involves single bonds. Generally, you've got amides that have that nitrogen next to a carbon-to-oxygen double bond. And then you've got nitriles, which have the C to N triple bond. So one important way to classify organic molecules is as saturated or unsaturated. So this topic that is called the index of hydrogen deficiency, or the IHD, is a way of referring to the degree of unsaturation of a molecule. So everyone's heard of saturated fats. What you may or may not have known is that what it means to be saturated is to have the maximum number of hydrogen atoms attached to that molecule. In other words, that means no double bonds. Anytime there's a double bond, instead of being bound to 2 hydrogens, 2 atoms get bonded to each other. And so whenever there's an extra bond, so no double, and I guess say no extra bonds. It could be double or triple. Whenever you have those extra bonds, the atoms connect to each other instead of to 2 hydrogens, and that removes hydrogen. So unsaturated there's a wide variety of how unsaturated, or the degree of unsaturation. But if you're unsaturated, you have less than the maximum number of hydrogen atoms, okay? And therefore, at least 1 multiple bond, or I should include, it could be a ring. So I'll put that up here too, no rings. So the IHD is a way of quantifying that, is a way of quantifying how unsaturated is a molecule. In terms of unsaturated fats, they refer to things sometimes as monounsaturated versus polyunsaturated. And that just tells you if there's 1 double bond or are there multiple carbon-to-carbon double bonds, but it doesn't really tell you exactly how many. So the IHD aims to be a bit more specific. The index of hydrogen deficiency, how deficient in hydrogen is this molecule? So the IHD refers to the number of hydrogen molecules, H2, it would theoretically take to convert the molecule into the corresponding saturated non-cyclic molecule. It's another bit of sort of useful structural information, along with these other techniques that we're going to learn about, mass spectroscopy, infrared spectroscopy, and HNMR. We haven't done those yet, but we'll get to them. So for simple things like alkenes and alkynes, or even cycloalkanes, it's relatively easy to determine their index of hydrogen deficiency. So To review just a bit, the alkanes have a general formula of CnH2n plus 2. So we did that a while back, but all alkanes have whatever their number of carbon, they have that number of hydrogens times 2 plus 2. So alkanes are fully saturated. They have all single bonds between carbon and hydrogen. And if we flip back, here's propane, that's an alkane. You can see that it has the maximum number of hydrogens possible. In terms of that general formula, it has 3 carbons. 3 times 2 is 6, plus 2 is 8. And you can see that it has the formula C3H8, so it's fully saturated. Okay? If you look at the corresponding alkene, however, for the same 3 carbons, it only has 6 hydrogens. So in terms of the index of hydrogen deficiency, how many H2s would you have to add to propene to make it propane? You'd have to add 2 hydrogens. You'd have to add 1 here and 1 here, 1 to each of these carbons, and you'd get rid of the double bond. So simple alkenes, when they have just 1 double bond, have an index of hydrogen deficiency of 1. And then alkynes have a triple bond, essentially 2 multiple bonds. That means you would need 2 hydrogen molecules to add back to this molecule to turn it back into propane. If you counted, you'd see that you only have 4 hydrogens. So you're missing 4 hydrogens off of what propane is. And so that means you need 2 H2 molecules. So alkynes tend to have an IHD value of 2. There are some cyclic ones that also fit into this thing. Whenever you have a cycloalkane, so if you have one of these rings, even though they're all single bonds, the fact that they've now connected to each other at the end of the molecule meant that now these 2 carbons are connected to each other instead of each having a hydrogen atom. And so they actually always lose 2 hydrogens if you're going to make a ring. If you count it, C3H6, cycloalkanes have the same formulas as the corresponding alkenes. So these 2 would have the same type of IHD value. In terms of alkynes, they end up having the same IHD values as cycloalkenes, because when you make a ring, you lose 1 H2 molecule essentially. And when you have a double bond, you lose another H2 molecule. So alkynes and cycloalkenes end up matching. So here are some more specific examples. It's helpful to think of the molecule and then think of the sort of target fully saturated non-cyclic alkane that it corresponds to. And then once you see the difference in hydrogens, it's fairly easy to figure out the IHD value. So this is the condensed structural formula for something like ethene, C2H4. You quickly apply the alkane formula, which is 2n plus 2, to get that it should have 6 hydrogens if it's going to be fully saturated. And therefore, you should have 6, you only have 4, and so the IHD value is 1 because you're off by 2 hydrogens. Okay. In the next one, if the formula is C2H2, you apply the general formula rule. So from here, 2 times 2 is 4, plus 2 is 6. That gets you to 6. The difference between 2 and 6 is 4. And so, let me do it over here. If the difference is 4, 4 divided by 2 equals, that's where the 2 comes from. Okay. Cyclobutane has C4H8. Well, if it was regular butane, it would be C4H10. The difference there is 2. And so 2 divided by 2 gives us an IHD value of 1. Okay. Now, notice if you check out the ones with oxygen, actually, oxygen really doesn't have an effect on the number of hydrogens. Anytime that you have an oxygen bonded, if it's all single bonded, then actually the molecule will have the same number of hydrogens that it would have had if it was just an alkane. So when you have propanol, 3 carbons, you should have 8 hydrogens to be fully saturated. And if you count, it still has 8 hydrogens because the oxygen bonds once to the carbon chain and then can bond to that normal hydrogen on the other side. If there are multiple bonds to oxygen, however, then that does affect the IHD value. So down here you can see this one, it has 2 carbons. 2 carbons should be C2H6. And so the target molecule is C2H6 with that oxygen tacked on. and that's actually the exact same formula as ethanol. So oxygen doesn't really affect the number of hydrogens that you should have to be totally saturated. It's going to be the same number of hydrogens as the corresponding alkane. Right? If I skip down to this one with the chlorine on it, in terms of saturation, halogens get treated like hydrogens because they are just simple atoms that form one covalent bond with carbon, just like a hydrogen atom would. When you're considering IHD values and saturation, you treat halogens as if they were hydrogens. So in this case, I have 2 carbons. So to be fully saturated, I need 6 hydrogens. And the combination of the 5 hydrogens and the 1 chlorine actually does add up to 6. So I would consider this to be fully saturated. I would say the target molecule is actually, it is what it is. The last one, and probably the funniest one, is nitrogen. When you deal with nitrogen, when you add a nitrogen onto an alkane to form an amine, nitrogen actually forms 3 covalent bonds normally. And so the nitrogen tends to have actually add to the number of hydrogens. And so we know that this is C3, and so it should be H8. But you can see that in this amine, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So when you have a fully saturated molecule that has nitrogen in it, it's actually the alkane amount plus 1. So it's a little bit funny, but that's probably the weirdest and most important rule that you're going to need to remember, which is that if I count this up, I would say, okay, well, 2 carbons, that means I should have 6 hydrogens in my target. But because there's a nitrogen, I know that actually to be fully saturated, I'm going to need 1 more than that. I'm going to need 7. So the target molecule I'm looking for is C2H7N. And if I count up between those 5 and these 2, I do in fact have those 7, and that would be an IHD value of 0. Last one here, 2 carbons. That would lead me to want 6 in my target, but because I've got a nitrogen, I add 1 to it, and so I actually know that the target should have 7 hydrogens to be fully saturated. Well, I've only got 3. That means a difference of 4, and divide that by 2 gives me 2 as an index of hydrogen deficiency. I think I'm going to give you some steps now, and we'll do a couple practice, but it becomes fairly straightforward once you do it, especially if you can see the structures. But if you have a framework to work with, I think that can benefit. So the first step would be to take whatever structural formula you've been given, if it's not written as a condensed structural formula, and sort of rewrite it like this. That was a really awesome circle I did around that formula. Okay, so once you've rewritten it, take the number of carbon atoms in the molecule and apply the alkane general formula to calculate the number of hydrogens you should have to be fully saturated. So that means take N and then do 2N plus 2, as I was doing in the examples up above. To get the exact target molecule, though, you have to consider what else is part of the structure. So if a halogen is present, you essentially can just add those halogens onto the formula and subtract those hydrogens out of the target molecule, because halogens and hydrogens sort of count the same in terms of saturation. If a nitrogen is present, you need to add 1 to the number of hydrogens in the target, and then add the nitrogens to the end of the formula. And if oxygen is present, just take the number of oxygens and tack it onto the end of the formula. It doesn't affect the number of hydrogens that you should have to be saturated. Once you've got your target molecule formula and you've got the actual molecular formula, you find the difference between the target and the actual and divide it by 2. And that will be the IHD value. Okay, so if we return to the same list of organic compounds, this is C3H8. It's the alkane. We know that's going to be fully saturated. This one is C3H6. The target, if it's C3 should be H8. Therefore, we're missing 2 hydrogens, and so that's an IHD value of 1. Right? On the next one, we see that we've got C3H4. We know that we should be C3H8, and therefore there's 4 difference. That means an IHD value of 2. Right? Benzene, we sort of did these ones before, so I'm going to skip ahead to benzene. Benzene is C6H6. The target molecule is C6H14. Therefore, we're missing 8 hydrogens, and therefore that is a IHD value of 4. The reason being it acts like it's got 3 carbon-to-carbon double bonds. There's 3 of the IHD values, but it's also a ring, which adds 1 onto the value. So you're missing 4 H2's worth of hydrogen. These two both have an IHD value of 0. They are all single bonded. C3 should be H8, but because I've got a halogen, the target is actually H7 plus that halogen. The halogens and the hydrogens add up to the normal alkane amount of hydrogens. So these both have IHD values of 0. Okay, the alcohols also, C3, I count 8 H's. So this is fully saturated, all single bonds. Same thing goes for this ether. The oxygen doesn't affect the number of hydrogens needed. In this case, however, target molecule, we would say, because it's got 3 carbons, there should be 8 hydrogens plus the oxygen. There's only 6 hydrogens, and therefore these both have a value of 1 because they're missing 2 hydrogens. In this case, we have 3 carbons, we have 6 hydrogens, and again, the oxygens don't affect the value of H's we should have. For 3 carbons, we should have 8 hydrogens, and since I only have 6, all of these have IHD values of 1. In these examples, 3 carbons should be 8. Since there's nitrogen, it actually should be 9. So my target molecule would be C3H9N, and because it matches that, this has a value of 0. In the next example, 3 carbons plus a nitrogen, so it should be 9 plus N. But when I actually count, I have 7 hydrogens, and therefore the difference is 2 hydrogens, and the IHD value should be 1. And in this case, 1 nitrogen, again, I'm going to add on to my target. So the target would be identical again. It's C3H9N. But when I count, I only have 5, and therefore I'm missing 4, which means an IHD value of 2. Slightly trickier are these larger molecules. We won't do all of them right now, but we'll do a bunch more in class. It's not really a new first step, but it's a more complicated first step, which is you have to figure out what the formula is by looking closer at what they've given you. And these are from the data booklet. So remember that at any corner where these 2 lines meet, that's a carbon atom. So I'm going to add in carbon atoms here, 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 and here. And all carbon atoms should have 4 bonds. So if you double check, this carbon has 4 bonds with this double bond here. This carbon has 4 bonds. That carbon has 4 bonds. This carbon only has 3. So there's actually an H sticking off of it to give it that 4th bond, even though it's not written in. And these ones have been drawn in for you. So now that you are looking at it a little bit more closely, you can count. It's got 1, 2, 3, 4 carbons in the ring, and it's got 1, 2 carbons there. So it's C6. If we count up the hydrogens, 1 plus 2 is 3. That makes 4, 5, 6, the one I drew in, 7, 8, and that's all I've got. So I've got 8 H's, 1, 2, 3, 4, 5, 6 O's. Okay, so here's the chemical formula of vitamin C, or ascorbic acid. That's the actual formula. The target is based off of that number of carbons, which is C6, times 2 is 12, plus 2 is 14. And the number of oxygens has no effect on the number of hydrogens that I should have to be fully saturated. So this is my actual molecule. Here's the target molecule, and the difference between 14 and 8 is 6. And if I divide that by 2, I get an index of hydrogen deficiency of 3 for vitamin C. Okay, here's thymine. It's one of the bases that's in DNA, the nitrogenous bases. Same thing, all the carbons have been drawn in here, so let's count them up. Starting on the methyl group, we've got 1, and then we've got 1, 2, 3, so that's 4, and we've got 5 carbons, so C5. I seem to have 1, 2, 3 more here. That's 5 H's, 6 H's. I've got 2 nitrogens, and I've got 1, 2 oxygens. Okay, so to get the target molecule, I take C5 times 2 is 10 plus 2 is 12, so H12. There's 2 nitrogens, so I have to add 1 for each nitrogen. So that target hydrogen actually is H14. And then I just add the nitrogens and oxygens to the end. So this is what the formula would be if it was fully saturated. The difference is 8 hydrogens. So 8 hydrogens divided by 2, my IHD value for thymine is 4. Okay, a couple more. Paracetamol or acetaminophen, the medicine that's in Tylenol. If we draw in our carbon atoms, this is a benzene ring, so we know there's a carbon at wherever these lines meet, so there's 6 carbons. Each carbon from the ring alone acts like it has 3 bonds. So this carbon up at the top has a 4th bond already, and this has a 4th bond already drawn in, but these don't. So each of these carbons actually has a hydrogen sticking off of it. It's just not shown in the drawing. So we're going to need to be aware of that when we draw out the formula. So if I count carbons, I've got 6 in the ring. I've got 2 there. That gives me C8. If I count hydrogens, I've got 3, 4, 5 on the outside, and then I have those 4 that weren't actually drawn in. So there's 9 total. That was a little sneaky. Then I count nitrogens, I've got 1, and oxygens, I've got 2. So there's the actual formula. The target is based off of 8 times 2 is 16 plus 2 is 18. But I have a nitrogen atom, so add 1, and then I'll put the rest back there. So the difference between my actual and my target is 10 hydrogens. 10 divided by 2 gives me an IHD value of 5. And thyroxine, the last example. Okay, I've got a bunch of benzene rings, and we'll try to do this as quickly as possible. We put the C's here, my ugly little trackpad C's. Any carbon here that doesn't have something sticking off of it should have a hydrogen, so there should be a hydrogen there. And this carbon also should have a hydrogen. That one should have a hydrogen, and that one should have a hydrogen. And these ones are also carbon atoms. The IB wouldn't give you a formula with such lacking number of carbon atoms, a structural formula like this, but this isn't in the data booklet anymore, so this is the best I could do. So wherever those lines meet, we know there's a carbon, and each carbon needs to have 4 bonds, so I'm giving it the appropriate number of hydrogen atoms here. So this is like a super duper challenge problem. I do not think the IB would ask you something like this, but we're going to see what we can, if we can do it anyways, and then we'll know we're fully prepared. So if we count up the carbons, I've got 6 carbons in this ring. I also have 6 carbons in this ring, and then I've got 1, 2, 3 more carbons. So it's C6H15. Count up my H's. I've got 1 here. I've got the 2 they didn't draw in, so that's 3. I've got these 2 that they didn't draw in, that's 5. Then I've got 6, 7, 8, 9, and I've got 2 here, so I've got 11. If I go through the other elements, I have 1 nitrogen, I have 1, 2, 3, 4 oxygens, and I have 1, 2, 3, 4 iodines. Pyroxene is pretty interesting in that it has iodine as part of its structure. Okay, so to do the target, C15 times 2 is 30 plus 2 is H32. The nitrogen adds 1, 33, but I have 4 iodines, so I can actually take 4 away from that because the iodines count as 4 hydrogens. So the target is actually 29, and then I'm going to add the rest of the stuff back in. So I have 11, and I should have 29 hydrogens to be fully saturated. That is a difference of 18 divided by 2 gives me an IHD value of 9. I'm nearly 99.9% sure they would never do something like that to you, but I'm cruel, and I thought we should give it a shot. So that is the IHD. Most important is to know your functional groups and organic homologous series, their names and their structures, and then just walk through those steps of sort of determining the actual formula, the target formula, the difference divided by 2 is the IHD value.